All right, so here we are, 19th of February. We're at class number 6. The down here, the red number, the red name is the main thing for today. It's not all we do, but it's mostly for me. So it cues me in that we're going to do the range equation today. Doesn't really matter to you guys, these dinos, although it does matter in the sense that, okay, Jackie, it does matter in the sense that, might as well talk about this now while I'm thinking about it. The homework this weekend, and it's a cold homework. So cold homeworks, it doesn't, well, for you guys, you being virtual, most of you being virtual here, that I'm going to have to do a catch up. So I'm going to make 5-2, which is a main sheet of packet 5. I will make you submit that, only virtual students. And you'll submit it on Wednesday, the 24th. So, okay, next week, 11:59, and it'll be worth at least 40 points, and that'll make up some of these points that the kids are getting in class for dinos. And if you don't do it, you'd have a 0 out of 40. So I'll try and limit the number, maybe only 2 pages per packet that you'd have to turn in, but this is a pretty critical one. As you can tell, we've been on it a while. And then you still turn it in with your packet, but okay. So that's the dino situation. Yesterday we did this one in class. This is from a screenshot. The type's land air. We talked about this yesterday, and today we're working on type 2A problems. So we're looking at this range today. The blue part, the part that gives you the height to this, this dash line is the Newton's first law, if the object were to keep going that way. And so the height of that comes from the first part of the second blue equation. That's the Newton's first law part. And the tax then is that second part of the blue equation. And that's what ends up with the purple, this purple delta y. And if you take the purple delta y all the way through time, you end up with this parabola. So that's diagnosed second blue, and really the second blue in all its glory. Another look at it. By the way, before we get started, yesterday afternoon, hopefully you got a chance to see this live. It was, they call it 7 minutes of terror, when you don't know what's happening. It's really about 12 minutes ago. So anything that we see on Mars, even one-way time, like the image Mars is sending us, like the fortitude, I should call it, but Perseverance, the image that Perseverance, even this video is sending us is like, depending on the time of year, but it's like 12 minutes old. Could be depending where Mars is compared to the Earth. But so let's say just 12 minutes old. So it's hard to see anything live, but as live as we could get it, we watched it land. It's animations, but then it gave us first pictures, which is awesome, of the surface of Mars. So I haven't been following it today, but today I'm sure they're starting to do experiments. They're going to drill down, they're landed in the lake bed. They think was full of water, so they should be able to find, if there's going to be life, even microbial life on Mars, they should find it somewhere down there below. And the helicopter, I'm not sure when it takes off, but they got about 30 days of helicopter work they can do. First thing they're going to do is just try and, it's only 4 pounds. They're going to let it in, so those things, they got to beat like 1,200 times a minute just to get enough lift, because of 1% atmosphere. There's not enough air molecules to hold it up. So it's not like a helicopter on Earth. So those things, those little rotors, there's 2 of them. They got to go in opposite direction because of conservation of angular momentum. But they've got to go at like 1,200 RPM or so just to get it to come off the ground. So they're going to try, and the first experiment is to try and get the helicopter to lift off the ground and then set it back down, and that's it. Let's see if we can just do it. And that'll be a miracle in itself, in my opinion. And then they'll start doing some tasks and heading out. And I really want to see that. To me, that's the most exciting. They're also going to put microphones on there so you can listen to Mars and hear it. You know, you can just, what's going on Mars? Not a whole, you don't hear a whole lot on Mars because at 1% our atmosphere, sound waves, you know, don't really travel. They need a medium. Sound waves need the thick atmosphere. So I don't know what kind of sound you're going to get, but we'll see. So they're doing all experiments. So maybe keep up with JPL, a Jet Propulsion Laboratory, for the next month or so. And then they're starting, the Martian crews come in and they have to, every day they're working on Martian time. So every day they start 40 minutes later. And so, like, you know, they'll start at 9 o'clock one day, then 9:40 the next day, then 10:20 the next day, you know, and then it keeps that. That's going to be weird. Their circadian rhythms are all going to be all screwed up. They'll be working at 4 in the morning, Earth time, you know. Now you got to talk about Earth time, Mars time. I'm sure there's an app somewhere. So, yes.
So I don't know if this is a dumb question, but why was the picture of, like, their first picture, why was it in black and white?
Well, I think, and that's not a dumb question because my wife asked the same thing. She said, why is it all black and white? Is it 1969 again or something, or what? I think transmitting that much data, they can then, with computers, they can go back and colorize it, but maybe somebody else can answer that question.
What it was is that was the sensor for it to drive. They've taken colored pictures now.
Oh, now they have, I haven't looked to see what happened today. So that was just, all that is the very first thing that it turned on its camera. So I'm surprised with its camera to drive that it wouldn't also be color. Why would that just be black and white? It's just a range finder kind of thing, probably. That's probably what it's doing. It's looking at range. And so it's just bringing back an image. Yeah. I think a lot of people, that's not a dumb question, Ayo. I think all around the world, people are going, why is it black and white? Okay. So Brandon says we have color today. Anyway, keep up with that, guys. And feel free to post stuff on Facebook because I won't, you know, I'm busy doing plumbing issues right now. So, all right. So yesterday we did 1 and 2A on sheet 5.2. So I gave you we talked about, you can see that the other classes, it gets a little hairy today, what we're going to do, because we're going to have to derive a new formula. So I warned you that it gets a little dangerous on 2B if you're using the half-tau method. Half-tau method works if we have type 2A, because in type 2A, you have that situation where at half the time, at exactly half the time, at half tau, half the total time, you're going to have the apex. You're going to have maximum height. So that works for type 2A, but students try that method on the test, and it turns out it's a type 2B problem and doesn't work. And we'll just start talking about type 2B today. Monday will be type 2B. Tuesday will be type 2B. And hopefully that'll do it. We can go on then to other things after that. I want to get on to, we'll get on to conservation momentum then maybe Wednesday next week. All right, so the safe method is, as we said last time, is use a third blue, and we would get, is that right? Yeah, yes, we would get this for our equation, and that works for type 2A. This works for type 2A and type 2B. Okay, so that's a safer way to always find height squared. So I'm not going to work that one. I'll let you, pretty much did work it. And then for 3, this morning, there were some students going, hey, we don't really understand football. And what? You're not Oklahoma? Well, some of you are from Oklahoma. You know, your football is soccer, what we call soccer. So let me quickly give you a 101 on football so you can work this problem. I wouldn't give you this problem on a test because that wouldn't be fair, obviously. But homework, I figure you can look it up or ask somebody. So 50-yard line is right here. It goes 10, 20, 30, 40, 50. Then it goes 40, 30, 20, 10, goal line. Okay, so then go up, down, your territory versus enemy territory. So he punts the football at the 15-yard line, which is, that's the goal line. So right there, it goes up and it comes over here. And somebody said, what, the 62-yard line? No, you go to 50, then you go back to 40, 30, 20, 10, goal, right? Yeah. To determine what yard line the return man should position himself on. Okay. So that's that. And I'll post a key, and there may be, I think there may be a video key of this. By the way, it's called now on Facebook, it's not called units anymore. For some reason, they decided to call it guides. Okay, I don't know why. It makes me nervous that they're getting ready to change everything, but they're calling it guides. And they made a big deal that they didn't change anything. Everything's still the same. People were freaking out. You don't do stuff like that and then not tell anybody. You know what I'm saying? I mean, that's just, and there was a time when there was nothing. There was no guide. There was nothing. Just disappeared. They must have got inundated with the emails. Profanity-laced emails. Mine was one of them. All right, so now let's do, before we do 4, get down here. Before we do 4, let's do 5. So 5 is the brunt of today, and that is to derive the range equation. Very, very useful, very, very dangerous, But daggone it, it's a shortcut and you just can't help yourself. Like, well, the shortcut around the river is to cross the river. Instead of driving 30 miles that way and 30 miles, I'm gonna take a chance and just cross the river. So that's what we're doing here. We're taking a chance and doing the range equation. The reason why it's dangerous is it only works for type 2A. But there's a lot of type 2A projectile motion. You know, a lot of things, football, baseball, whatever, you throw the ball, whatever, Fort Sill, you shoot off the cannon. I mean, it ends up landing at about the same height that it took off at. And so range is a pretty good approximation. Okay. So let's do this thing here. By the way, this will be something you'll have to derive on the next test. So I have a nice laid out derivation, but let's just do it together. So we'll attack it like we attack any kind of projectile motion problem. First, the red. So we say, okay, but it's kind of a special red. It's delta x sub r, okay, meaning range. And that equals V naught cosine theta. Okay, remember, if something's lifting off here, and something takes off with type 2A projectile motion, it takes off, its initial is right there, its initial velocity, but there's going to be a blue component and a red component to that right triangle, and the blue component is the y, and so this being theta, and we'll keep theta as from the horizontal. So horizontal is cosine, so v naught cosine theta times tau, because we're talking total time, okay, all the way through. And matter of fact, before I forget, on this right here, on the equation sheet, I've had this equation sheet for 10 years. I wrote this thing, and I've always called that T, but that's kind of dangerous because really it's tau. Okay, it's total time. You can find total time using that formula. Anyway, let's go back. So then in blue, we'll start with delta y, second blue, delta y is equal to V naught sine theta tau minus 1/2 g tau squared. Okay, good so far. We're trying to find out what the formula is for the range. So let's go ahead, and what we're going to do, our strategy is to go ahead and get this in terms of tau, and then we'll just substitute that in right here. That way we can find the range without having to know the time. Like if you're at Fort Sill and you're wanting to shoot off your Fort Sill down in Lawton, and you want to shoot off your ballistics, your missiles, whatever you got, your cannons, you can't go do a test shot and time it. You want to know what is my range going to be just from knowing what the angle is, that kind of thing. Okay, and your muzzle velocity. So the thing about type 2A is the delta y is 0. So I'm going to replace that. I'm okay if you start this way. Delta y is 0. Are we buffering or something? Okay, so delta y is 0. So that's 0 because it's type 2A. So if that's the case, we have V naught sine theta tau equals 1/2 g tau squared. So what can I do with one of those taus?
You can divide both sides by tau.
So you can do that as long as tau is not 0. Well, obviously there's some time. So take out the square there. So now we have that. And then I'm going to go ahead and solve for tau. And this, you already have this equation. Tau then is 2 V naught sine theta all over G. Okay, now I'm going to take that. I'm going to set, this is what you got to do on the test. Not till March, but I'm going to substitute that in for tau. Remember, the test next Thursday is just over 4B. None of this stuff's on that test. All right, so let's just go ahead and plug the whole thing in. And I'm going to make this black because this is not red or blue. So we have delta x range equals, that's kind of messy here at first, V naught cosine theta 2 V naught sine theta all over G. Well, that's kind of a mess. Let's clean that up a little bit. So my range delta x sub r is V naught squared 2 sine theta cosine theta all over G. Now the cool part. This right here is an algebra identity. It's actually a trig identity. So I didn't think second hour had it, third hour had it, but after I showed them, they all raised their hands and said, yeah, we have seen this. So I know a lot of you have seen this. So this is equal to something, like identities, like sine squared plus cosine squared equals 1, those kind of things, or law of sines, law of cosines. When you learn all that stuff, you also happen to learn this one. Anybody know this one?
Sine 2 theta, right?
Sine 2 theta, very good. So there's 2 points there. This is called the double angle formula. And so this is equal to sine 2 theta. Okay, so then we put it all together, and in all its glory, the range equation looks like this. Delta x sub r, meaning total range, is equal to V naught squared sine 2 theta all over G. And that is really useful, but at the same time, like I say, really dangerous. So range equation. And if you ever go to Fort Sill and join the Army, you're going to use it all the time. Range equation. Danger. Skull and crossbones. Okay. Will cause extreme tire damage here. When you try and use this, only use it for type 2A. Only type 2A. I know on the test, students, they warn them every year and they're still going to do it. They'll use it for type 2B. This is the danger of just memorizing formulas. That's one of the reasons why I stopped I used to have kids had to memorize all of these formulas. I thought, well, that's what I did. But that's dangerous. What stopped me doing that is I had two girls that were twins, and they were really good students. I loved them, man. They're great kids, but they memorized. They had photographic memory. They could memorize every step here. Boom. But the thing is, they had no idea what they were doing. So they were experts at memorization, but but physics isn't about that. So when it came time to actually use the problem, they didn't know. They had all these equations in their head, but they had no idea when to use them. And so that forced me to say, I mean, on tests, kids could take a note card, they could write anything down they wanted. Well, about half the kids would, and half the kids wouldn't, and then the kids that wouldn't just flunk because that's why I started giving equation sheets to kind of balance out the field there. So the point to that is that, yes, it's a good equation, but very dangerous. My twins would use it always in the wrong spot. So they ended up getting A's because they did all the extra work, right, in physics, and they go back and do makeups. Back then we didn't have red, black, and blue, but we did something called second chance. So they do that, and then they got A's. Then the next year they signed up for AP Physics. And going, oh no, because they like me and I like them, and it was fun. But oh my God! So they struggled through AP Physics, but they got through it. And I think they still got A's because there's all kinds of ways to get your grade. Then it came time for the AP exam. I thought the best they're going to do is a 2 out of 5. They got 1s. And I could see it happening. I knew it was going to happen because in physics, if you don't step back and know the situation, that's why I started saying, okay, red equations, blue equations, orange equations, trying to help you organize your thoughts into colors. Because if you're just given a mess of equations, you're going to blow it. Okay, so word of warning, don't worry so much about the equations. You'll get an equation sheet. Look at the problem from 10,000 feet. Say, okay, what kind of problem am I in? That's why finals in physics is so hard, because when you're doing a test, okay, that's still a limited amount of material. We're in projectile motion, so you're kind of in the range. But on a final, it's like, oh, it all holds, it can be anything. And people it's hard. You guys got lucky first semester, they didn't have finals in physics. But second semester, I think we'll have a final. Okay, but I try and limit the damage there too. So here we go. This next one kind of got wiped out, but this is the right one, right? Yeah. So it says a modern day tank fires a shell. So now we're going to use the range equation. It says, what angle must the gun be at to be fired to achieve maximum? Oh, okay. Let's go back here real quick. What angle would I want? Okay, back up. Let's go back to this. Go back to this. This is an equation sheet. This is off equation sheet number 9. And let me erase it a little bit, clean it up some. But I have this sine and cosine. This is a unit circle. You guys have heard of the unit circle, I guess. But this is the sine version and the cosine version of the unit circle. Sine for us is vertical, cosine is horizontal. That's fairly standard across physics. So what is the maximum value of sine? What's the biggest sine can be? Can you have sine of theta equal 2?
No.
Did you say 1?
1 is it. It's a unit circle. So sine of theta, cosine, the maximum it can be is 1. Now, for sine, for it to be 1, it's a little blurry here, I apologize, but the angle is 90 degrees, right? Because that means it's straight up. And sine's measuring how far up it is. Cosine, 0 is 1. Cosine's measuring how far to the left or the right it is. So the best you're going to do on sine is 1. So going back here now to this for range. So going back to the range equation, what is the best? What angle do you want to achieve maximum range?
90 degrees.
90 degrees is what you want, but therefore, what is theta?
$45.
Right, because sine, it's double angle formula. So sine 2 theta over g. So if theta equals 45 degrees, you're at maximum range. Over here, you're going to go as far as you can go if theta is 45 degrees. Okay, and that makes sense. I mean, if you're punting a football, say you're a punter, staying on the football theme here. If I'm trying to punt for maximum range down the field, if I'm sitting on my own 20-yard line, I want to get that ball. So I'm going to punt the ball. They just know this instinctually. But if I'm if I'm at my opponent's 40-yard line and I want to pin them deep, right, like at the 5-yard line, then I'm going to punt it like at 60 degrees. It's going to come up and then come back down like there. 80 degrees or something like that, come back down there. So, and then if you go less, if you go 30 degrees, it comes up and comes down like that. 20 degrees comes up and comes down like that. But the maximum range you can get is 45 degrees, if that makes sense. And it makes sense with the equation because sine of 2 times 45 is 90, sine of 90 is 1. So on this problem, delta XR, we're trying to go maximum range for this incredibly fast shell. That's not a made up number, that's a true number. V naught squared over G is what I need. So it says, what's going to be the maximum range? Now, assuming air drag, of course, is 0, but so I have 1,700. That is a mile a second. And that's how fast I looked it up when I wrote this problem. It may be faster than that now. 1,700 meters per second squared over 9.81 meters per second squared. And that'll end up with meters, right? I don't know what that is, but it's a huge number and it seems absurdly large. And the reason is it isn't really that great because it's not really that far, because this is taken into account, or this does not take into account wind. It doesn't take into account air drag. I mean, air drag itself, and we've seen this formula before on gold standard, but air drag itself is R sub A equals 1/2 D rho A V squared. So V squared. So that for this particular thing, that's 1,700 squared right there. That makes the air drag huge. Now the bullet, the shell's got a low profile. That's that. The density of the air is still it's 0.0012 grams per cc. That's still pretty large. And the D is probably about 0.5, the drag coefficient. So for a shell coming off, it seems just pure range equation. You think, oh man, I'm going to go destroy, Noble with my big cannon here. But then air drag comes in and it wipes you out at that high speeds. So we'll get to that. We'll get to air drag here later on. Okay, so that's how you work that problem. That's number 5 done as well. So that takes us to the back. Oh, one other thing we got talking about this morning was physics engines on video games. Like in Call of Duty, I was asking the kids, I don't really play Call of Duty. I did with my sons, but that was a long time ago. But I said, do they take into account air drag? And they said, no, they just have a drop. There's a drop, a bullet drop, which takes into account gravity. Okay, gravity. Maybe they throw in a little air drag in there too. I don't think so. I don't know. But if you have a sniper game, you ever played a first-person sniper game, that takes into account other things a lot more. The physics engine is just built into, temperature, air drag, wind, all that stuff you have to take into account. Cade Wagner, I had him last year. He shoots rifles for sport with his dad, and they fire at targets. And he came in and told me that they'd set up almost like a 3/4 mile range. And now I go to the range and shoot pistols, and with pistols, it's like, you're shooting close range. The guy's like 30 feet away. But then I'll shoot my buddy's rifle sometimes. And then you do have to kind of take into account bullet drop. But he's now looking 3/4 mile away. And so now you got curvature of the earth is going to play a role. And you can adjust that on the scope. He says you look through the scope and you can adjust. It automatically computer adjusts for that kind of stuff. Then you got to take into account wind. There's a little anemometer. You got to hold up for wind. You got to take into account air drag, all that kind of stuff to try and hit the target. So it's like physics, like an operation in physics. You know, I told him to give me some videos, so he hadn't yet. But so anyway, but my point is, there's a lot in a physics engine in a game, all that stuff. If you want to be a game designer, and you want to really make a lot, that's a lot. Blizzard out in LA. I have a buddy that works for Blizzard. They work you to death. They're putting this guy 70 hours a week. So watch who you work for. But you can build physics engines for video games. They're just getting better and better and better. If you look at Grand Theft Auto, the old ones, the car would like flip like 20 times, you know. And now they take into account angular momentum and all kinds, you know, conservation momentum, all these physics principles. What we study. It's not quantum. It's not relativity. It's just what we study. Those physics principles, if you know those, you can mesh them with your computer knowledge, you can be a very valuable person in the gaming world. So consider that if you love video games and stuff. The last thing I want to talk about is the homework. So the homework, it's a cold homework, which means that, yeah, it's due Monday, but really not due Monday. No harm done. Of course, for you, it's really due Wednesday because you're virtual. But for the students in class, I'll come around Monday. I'll give them extra dynos if they did it. Okay, so let me just talk about this. The reason why these are cold is this is all the whole back is type 2B. Sorry, Pepper's whining. She's crying back there. She's stuck. Where's Pepper stuck today? Yeah, see, it doesn't take much to stick Pepper. No, she got out of that one. A little cord. Put a little box like this tall, Pepper stuck. She can't get over it. All right, so back here. Well, being blind and deaf and then have dementia, it kind of puts you at a disadvantage. So on this one, let's at least set him up. Joe Dynamo disarms an ISIS operative. So he's on top of a roof or something. And the thing is, here he throws this thing off the roof and it's 30 degrees. So he's throwing this thing up at 15 meters a second. Sorry. At 15 meters a second. My angle's probably not right, but so V naught, the hypotenuse is 15 meters a second, and the angle is 30 degrees. But the thing is, this thing comes up and then lands down here. So you have this delta Y that is negative. The delta Y, do we know it? Yeah, parking lot 10 meters below. So my delta Y is equal to -10. And these really aren't that bad. The only thing about these problems is that you don't get any kind of shortcut. Like with type 1, V naught Y was 0. With type 2A, delta Y is 0. So with type 2B, no shortcuts. You still use the red and the blue, mostly red and second blue, but it's, you know, full Monty. And then when you get down to 7, now we got Slappy the Clown is being shot out of a cannon. And so once again, he's going to end up landing below. I told first hour wrong. I thought he landed above. I feel bad about that. First hour gets burned again. All right, so he's fired up at 40 degrees above the horizontal. So he's fired up like this, kind of like Joe Dynamo. So now that's 40 degrees. The speed is 68 feet a second. I don't know why I picked that weird number. 68 feet per second. See, Pepper's stuck again. If I can show you Pepper, let's see Pepper. Where's Pepper? There she is. She's back there in the back. And she's stuck in that little box. See, she's in a little tiny box. And that was enough to totally bamboozle her. So I will go save her. She'll cry until I come. Right. Aha! She got out. Pepper's on a roll today, man. She's doing good. So we come along here. She's doing really good today. The small net is located 200 feet horizontally. So this distance here, delta x, that is delta x. Delta x is 200 feet. So you know that. And that's it. And from there, you're supposed to find out whatever. Okay, so there's your homework. A couple of hints on there for Monday. Doesn't matter to you guys, you're virtual, but the question came up, would we be at school on Monday? You know, I'm going 50-50 because three things. One, these roads, I can get on my driveway, but the streets are still really bad. I'm watching cars slip and slide over the place. Two, the parking lots at the high school have not been cleared as far as I know. And that is a priority, but it's more of a priority to clear streets. Three, there's all kinds of water damage, I know, in the 200 hallway because of bursting pipes. And I'm assuming more pipes will burst. So my guess is, if I had to bet, I'd buy 60-40, let's say. I'd bet that we don't. Tuesday's 50-50. Monday 60-40. Okay. For school. Well, I'm not going to end it. I'm going to say goodbye. And anybody wants to stick around and talk about anything can stick around. But I'm going to turn the recording off. Unless you have a question. Any questions?